we're ready for the second talk of the day. The second speaker is going to be Pablo Sobuchiski. He will speak about rewriting modulo symmetric monoidal structure. And Paweł, when you're ready, you can take the stage.
Thank you very much, Ivan, and thanks for the invitation. Can you hear me okay?
Yes.
So I'm very happy to be able to talk here. So I'll tell you about some joint work that I've been working on with these four people, Filippo Bonchi, Fabio Gaducci, Alex Kissinger, and Fabio Zanazzi. And we've been working on this now for around 6 years. So it's kind of a long project. It didn't seem like it was going to be a very long project at the start, but it turned out to be, there's turned out to be lots of interesting things here. So I'll start off with just a very kind of high level introduction to maybe the reasons why I find this area interesting. And then I'll state sort of the main problem that we tried to solve, at least from the start, because in the end, I thought about what to include in this talk, and I'm only really including results from the first paper that we had. But I'll tell you at the end a little bit about how this has continued and what we are still working on. And of course, if there's any questions at any point, please feel free to interrupt me. So this talk is about string diagrams, right? So maybe I'm going to start in a slightly grandiose PR kind of way to say that what I really find fascinating about string diagrams is that they kind of go beyond what, let's say, classically mathematics or the way that classically mathematics has been done. So you could argue that since Fibonacci, essentially the way that mathematicians calculated has been with these linear terms to perform the computations. And these are understood as denoting maybe perhaps elements of some algebraic structure, maybe which has a presentation with a signature and some equations. And in the 20th century, these things were sort of very carefully formalized, starting in the 19th century with logic and universal algebra. Lauvier came along and told us that sort of these terms, we can understand them categorically. They actually are the arrows of a free category, so the free category of finite products on some signature. So they are kind of an interesting, if you want, combinatorial characterization of some universal property of this free category. And a lot of computer science has been concerned with various computational problems associated with these data structures, if you like, right? So for example, the word problem, and these are often handled with term rewriting, and term rewriting itself is a very rich discipline of computer science with thousands of papers. And this is important, right? So this makes its way into tools, and this is used in various applications. So what's wrong with classical terms? Well, terms are, when you think about them, they are kind of restrictive, right? So terms have a built-in assumption of Cartesianity, right? So first of all, whatever you're talking about, you're assuming that it's copyable and discardable. And moreover, this data, which is copyable and discardable, is transformed in a functional way, right? So the operations are total and single valued, right? So you can get around this in various hacks, but in the end, this is built into the notation. This is built into the notations that we use. And of course, these assumptions are not particularly fit for purpose nowadays. So if you look at quantum foundations, of course, data isn't classical, and computing functions are total very often. And if you're interested in sort of thinking about computational systems of various kinds, and you want to break them up and understand how they fit together from the pieces, these pieces typically won't have functional behaviors. They'll be more like relations. Okay, so for these various reasons, terms are not quite satisfactory. So some solutions. So in computer science, especially in recent sort of 10, 15, 20 years, There's been various people studying linear type theories. So the basic, very high level explanation is that we basically disallow some terms. We say some terms are not well formed, right? They're not typable. But I don't think that this will, at least this doesn't often address all these limitations. And the solution that I would advocate is to make the jump from terms to string diagrams. And when I say string diagrams, I mean string diagrams for symmetric monodal categories. But of course, this involves work, right? So a lot of this 1,000 years of history of people getting used to dealing with normal terms, ordinary terms, doing calculations, coming up with algorithms, all that stuff has to be looked at freshly. And in this talk in particular, what I would like to understand is how to formalize and perhaps mechanize these actual sort of calculations that you would do with pen and paper. So why string diagrams? Why do I think string diagrams are good? Well, first of all, they are a conservative extension of classical terms, right? So you can, anything that you can do with classical terms, you can do with string diagrams faithfully. And this is because of a very cute theorem proved by Fox in the 1970s, that a category of finite product is nothing but a symmetric monodal category with a commutative comonoid structure on objects that is natural and coherent. Okay, so essentially, I'm going to explain what this means with string diagrams. I'm just going to, for most of this talk, I'm just going to assume one type, right? So my wires in my diagrams are, by the way, can you see my mouse pointer? Is my mouse pointer visible?
Where is it in your opinion?
Cannot see.
Yes, I can see it. It's on the fork.
It's very small, but it's seeable.
Ah, yes, now it is.
And it's black.
I wonder if I could make it bigger.
What's black over black?
Yeah, I apologize. I don't know how to fix it. But okay, I'll just do my best. I'll wave it around. Oh, okay.
Yeah.
If I wave it fast, it gets big. Okay. So I'm just going to, for most of this talk, I'm just going to assume one object. So one type. So things built from one object. So my wires are the objects. And this is a picture of the co-multiplication, and this is a picture of the co-unit. So the commutative comonoid structure just means that you know, I have associativity, commutativity, and unitality. And the idea that everything commutes with everything is not. I mean, this is a natural thing, means that everything commutes with the structure, right? So you have these equations over here. And basically, because of this this realization of Fox, you can kind of encode any algebraic theory as a monodal theory in this sense. And perhaps it's not so obvious from just this slide. So I made just a little example just to give you the feel of how this looks like. It's one slide too many. So let's say I take the signature of monoids. So I've got a binary multiplication and a unary unit. This is kind of a term that you would, you know, that is a classical term. Okay, it's not written in fix, but I could easily write it in fix. And the idea is basically that instead of this term, we're going to draw a string diagram. You see this diagram here, this term has one variable, one free variable, and a free variable is kind of like an input wire to the diagram. This variable you see appears twice, so we first copy it, and then we feed it into the various operators corresponding. I mean, you can see, hopefully just by staring at this, you can see how the correspondence works. And then of course I can encode the, let's say, equations of the theory of commutative monoids as particular string diagrammatic equations. And there's some additional equations that I need that essentially are saying that this symmetric monodal category is actually going to be Cartesian. And essentially what these equations mean is the first one here says that the multiplication of the monoid is a total function. This says that the unit is a total unary operation, which means it's an actual element. So if it was undefined, it would be nothing, but this equation tells you that it's defined. And these guys tell you that these things are functional, so single valued. So multiplication is single valued, and the unit isn't one element. It's not more than one. Okay, so I mean, this slide is just meant to give you a feel for how this correspondence works. But let me just give a little advertisement for a recent paper that's come out with Fosco, Ivan, so two of the organizers here, and my PhD student Chad Nestor. So we've essentially extended this kind of we have a kind of a Fox theorem, but not for categories of finite products, but these things called discrete Cartesian restriction categories. And discrete Cartesian restriction categories, they basically have the co-monoid structure, but also the multiplication of the monoids, which, okay, it's kind of like a semi-group. It doesn't have a unit, right? So the thing that's missing here is a unit, but it is associative and commutative. Moreover, we have the special Frobenius equations. So I noticed that this is the second time special Frobenius comes up today. And we have kind of a half naturality, right? So we have naturality with respect to the co-multiplication, but not necessarily the co-units. And just as before, I told you that a particular class of string diagrams gives us a nice syntax for classical algebraic theories. Now, this class of string diagrams will give us a syntax for these things that we call partial theories. And these are the same, turn out to have the same expressivity of essentially algebraic theories. Basically, the idea is that we, do the Lorvier functorial semantic story, but instead of sets, we take the category of sets and partial functions as the universal models. So essentially, you can define, theories in which operations are partial. And you can go one step further and think of this notion of Cartesian by category of relations due to Carboni and Walters as a kind of algebraic theory. But these algebraic theories are even more kind of expressive because instead of the category of sets and instead of the category of sets and partial functions, we take our models in the category of sets and relations. Okay, you can see this is kind of an extension of the story on the previous slide because now we also have a unit. We have everything is as you'd expect. We have the special Frobenius, and we have this. We don't have any kind of naturality anymore, but we have this kind of a idempotence of the convolution, if you like. And this gives a just as this notion of partial theory gave a notion for kind of essentially algebraic theories with partially defined operations. This gives you a richer syntax for things that we call relational theories, and they turn out to have quite an interesting sort of variety theorem that's recently been showed by Chad Nestor. And in recent years, there's been a whole load of applications of string diagrams, so various approaches to quantum foundations, ZX calculus, other string diagrammatic calculi. I got very excited a few years ago that you can do linear algebra with them, so I wrote a blog about this. And these various other papers. I think I've probably given you enough of a motivation for why I find this interesting. So let me just maybe move on because I don't have so much time. I want to give you just a little bit of an intuition of how you calculate with string diagrams, how you actually use them with sort of pen and paper if you haven't done this before. And the idea is very similar to kind of the way that we would work with terms. The idea is that this is a little string diagrammatic proof showing that multiplicate in a commutative monoid. If I just take as an axiom that the unit cancels on one side, then it's also going to cancel on the other side. Okay, so the first thing I do is I use the law of symmetric monoidal categories to push the co-units on the other side. Now I notice that I have a match of the left-hand side of an axiom. So this just tells me that this is commutative co-multiplication. So I can replace the thing in the, in the yellow box with the right-hand side. And now I notice again that I have a match because I have the axiom that the unit cancels, and I can replace it with that entity. Right? So this is a little proof. So some people call this string diagram surgery. The basic kind of general idea is that if I have an axiom that says L is equal to R, then when can I use it? Well, the idea is if I can if I start with A and I can decompose A into something that contains L in the middle, and you notice that in the symmetric monoidal category, I can always put things into this form, then I can replace the L by R, and I conclude that A is equal to B, right? That's the kind of basic general situation here. Now, of course, I said before that when you want to compute, the usual thing that you do is you take a system of equations and you orient it, and the system of equations becomes a rewriting system. Okay, so we can define a similar thing here. So a rewriting system on a symmetric monoidal category will just take as our rules pairs LR, where the L and R have the same domain and codomain. And now if I have two arrows in my category, I can write that A rewrites to B when there exists a context such that A can be split up into something containing A, and B is the same thing. Sorry, this is a typo. This should be A1 and A2. The context stays the same, but we replace L with R. Now, the fundamental question of this talk that we'll be interested in is how do we formalize string diagrams and how do we compute with them, right? So how do we take these things off the paper of things that you just do with pen and paper, and then maybe you even nervous about it and you translate everything into classical terms, but we want to really compute with them as a syntax because of the kind of useful applications that this world has. So if you look at the classical topological descriptions, I'm thinking of things like Joao streets. They're not particularly easy to turn into a data structure, right? It's something that you could code up on the machine. And the main thing that really does the job here is this thing that we discovered, which is a characterization. So just as Lauvier described the category, the free category of finite products as something that has terms as arrows, we can describe the free Cartesian bicategory on a signature in a combinatorial way as certain hypergraph-like structures. And this is what I'm going to explain in the next part of the talk. So I'm going to tell you about hypergraphs, and then I'll tell you about the mechanism of rewriting, which is this thing called DPO, which stands for double push-out rewriting. Are there any questions, or should I go on? I'll go on. So let me tell you what a sigma hypergraph is. So a directed multi-hypergraph is something that contains vertices and edges. The idea is that these are just like directed graphs, except an edge is allowed to have a word of vertices as its source, and a word of vertices as its target, right? So these are ordered lists of tentacles, that the input tentacles and the output tentacles. So you can then consider the category of hypergraphs and hypergraph homomorphisms. And it's not very difficult to see that just as the ordinary category of directed multigraphs is a pre-sheaf category, the same idea translates here. We can describe this thing as a pre-sheaf category. This thing will have the objects for the vertices, and instead of having one object for the edges, we're going to have natural numbers times natural numbers of such objects, so M and N are natural numbers, and then this tells you this is going to be the set of hyperedges with M input tentacles and N output tentacles, and you're going to have correspondingly many source maps and target maps. Let me try. Now, so these are just ordinary the category of hypergraphs. Now, if I take something like a model signature, so something where I have operations that can have some arity and co-arity, I can identify this with a one vertex hypergraph, and then I will consider hip sigma to just be the slice category of hip over sigma. This just basically means that I consider hypergraphs where every hyperedge has been labeled with an operation named for of sigma, okay, and it's of the right type.
Paweł, can I interrupt you for a moment?
Of course.
So there is a question from the audience. I will just read it because I don't understand it. So they ask you, so that's like pre-nets tensor schemes, but I think it was referred to this slide we have in front of us.
Yes, there's a definite connection of pre-nets. In fact, I think pre-nets, these are also things that I think, yeah, you could also think of these things. I think Bob Walters called them monoidal graphs. But yeah, these things are definitely connected. I'm going to call them sigma hypergraphs. And I'm going to be particularly interested. So we know that this is a pre-shaped category, so these things are very well behaved. Hips and in particular, because hip sigma is a slice, things like push-outs are going to behave well. So I'm going to call CSP hip sigma to be the prop. So this is a strict monoidal category, strict symmetric monoidal category, one object. The arrows from M to N, so the objects are basically of this proper natural, of any proper natural numbers. So the arrows from M to N are isomorphic classes of cospans of this form, right? So I have a hypergraph in the middle, and I treat the natural number M as a discrete hypergraph of M vertices, and similarly for N, and I consider cospans like this at the arrows of this thing. Okay, so we have this this particular prop of cospans, and when the idea is when we compose arrows in this prop, we're gluing these hypergraphs along this common boundary. The other thing I want to tell you about is this prop of special Frobenius algebras, and this is generated from the signature of we have comonoids, monoids. Both of these structures are commutative, and they satisfy the special Frobenius equations. Now, the central theorem here is that, and the theorem that kind of makes everything run is that I take some signature sigma, and I consider S sigma, okay, there's a missing subscript here, S sigma to be the free prop on this, okay? Then I consider the co-product in a category of props. So essentially I take my S sigma and I just add to it a Frobenius structure, special Frobenius structure. Then this is isomorphic as a prop to this prop of cospans. And I have to say, I forgot to write this down, but this is a generalization of a theorem that was proved, I think in the late 90s by Roseborough, Sabadini, and Walters. They were considering the case just for directed graphs, but it generalizes to arbitrary. So directed graphs, that would mean that my sigma just has a single unary operation, but this generalizes to any signature. So how does this work? I'm just going to give you some examples just so you get a feel for this, right? So the idea is that the thing you see on the left I'm going to think of them as string diagrams, and then I'll tell you what these string diagrams look like over here. So the idea is that this is a string diagram. It has one input, one output. I'm using the signature here, which is the signature of a monoid, just to keep things simple. So this guy here would just translate to the hypergraph that looks like this. I'm sorry if the drawing is a bit messy. So this is the hypergraph with 3 vertices, and the edge is connected like this. It should look similar to the thing on the left. And then the boundaries are just single, sort of singleton vertex sets, and they point out the vertices that sort of stick out, the ones that the dangling wires over here, if you like. But of course, this is in this thing here, we also have a Trebenius structure, right? So we have this Trebenius structure, which I'm going to always denote with these filled in nodes. So for example, I have a string diagram like this. So what is that going to look like? Well, it's going to be the case, this is going to be used in the case where sort of both of the tentacles of this edge, of this hyperedge, connect to the same vertex. And again, the similarity, the sort of looking at both sides in this table should give you an idea of how this works. And you can sort of be even more tricky. So here I have, I'm using a lot of the Frobenius structure. I'm basically sort of connecting everything around here in the loop. And this would be, and there is no boundaries here, right? There's no dangling wires. So this is just going to be the closed hypergraph where this hyperedge has all its tentacles connected to the same vertex. And this is kind of exciting, right? Because we have this on the left here, we have string diagrams in this guy here, and on the right we have these very concrete things, the hypergraphs together with some functions that pick out vertices, and these are things that you could easily encode in the machine. So having characterized certain string diagrams as hypergraphs, we can now use graph rewriting to perform string diagram surgery. Okay, and it turns out that the right notion of graph rewriting is this thing called double push-up rewriting, which was originally developed in the 1970s by Hartmut Ehrig and others. And we're going to use a particular variant of this, which is DPO with interfaces, or DPOI. And this, I think, this was originally studied by Gaducci and Heckel, but then was used by also Ehrig and Hartmut and Barbara Koenig in 2004, and their work on borrowed context. And also, this was something that formed a significant part of my PhD thesis, so it's something that I know quite well too. So let me just give you a little tutorial on what DPO is all about. I guess that probably not everyone here has heard of this stuff before. So the idea is that this is going to be a rewrite system on graph-like objects. Okay, so I'm going to just keep the category anonymous for now. Just let's say we're in a well-behaved category with push-outs. Okay, so the idea is that a DPO rule is going to be a span of morphisms, and the idea is that the L here is the left-hand side that we're going to try to match in our the thing that we want to rewrite. The R is the right-hand side, and K is some kind of context of the stuff that stays untouched. So an application of this rule is a diagram consisting of 2 push-outs. So this M here is the match of the left-hand side in C, and then the existence of these 2 push-outs kind of tells you the mechanism of going from C to E via this rule LKR. And if you want some kind of operational intuition, sort of to rewrite C to E, first we need to find this match. Then at that point we have these 2 morphisms, so we need to find an object D such that one is a push-out, so this is sometimes called a push-out complement. It might not exist. If it exists, you got lucky and you can perform the rewrite. And then you perform the push-out to get to E. So let me give you a worked example now. So this is a spoiler. This is a rule that's going to kind of be like an oriented equation that tells you that, you know, you think of this as multiplication in units, right? So this tells you that if you multiply something with a unit, then you get the identity. So this is how this rule is going to look like, but let's just forget about the intuition and actually work through this double push-out construction, again, just to give you an intuition for this. So here we have a larger hypergraph over here. Now we can find a match, right? There's a hypergraph homomorphism from here to here. And then when you, the idea is that this guy is going to be like this guy with the left-hand side deleted, essentially, right? Because that's what it would mean for this square here to be a push-out, right? So if I just take away this part, I end up with this. And now my right-hand side is just going to collapse these 2 points into one point. So I'm going to glue them together and end up with this right-hand side. And when I explain a little bit more properly about how these will correspond to string diagram, you know, sort of string diagram rewrite rules, this is exactly going to correspond to something like the following derivation, where here I started with a string diagram like this. Remember that this filled-in structure is sort of part of the Frobenius structure. I find my match here, and I replace this with just the identity y, and I end up with something like that. And please interrupt me at any point if something isn't clear. Okay, oh my God, this diagram looks terrible. It looks very busy, but okay, let's work through it together. I just want to give you an example of the fact that the push-out complement might not be unique. Okay, so here we have a particular rule. So this is a rule that on the left collapses these two vertices, and on the right glues this red guy in between, this red 1,1 hyperedge. Okay, so there are two different push-out complements that will result in two different final diagrams, right? So one is the yellow. If you look at sort of the yellow part of the diagram, here we can obtain a push-out complement just like this. So essentially what I'm going to do here is I'm going to glue this red hyperedge alongside this blue hyperedge. But also if you look at the green part of the diagram, that's another push-out complement. So I've reversed the 1 and 2. And so essentially now I'll glue the red guy, but I'll glue him in a way so that he's facing the other way from the blue guy. And this again corresponds to some interesting sort of special Frobenius business, because if I start off with this rewrite rule that from the identity I can replace the identity anywhere in my diagram with this red guy, then if I start over here, which is kind of the string diagrammatic equivalent of this guy here, then I can glue the red guy on this identity wire. So I end up with this string diagram, but I can also do some additional Frobenius tricks and kind of insert another loop in, and I can now glue him in there. And these are not the same diagrams, right? These are not equal. So again, there seems to be some intriguing correspondence between sort of these double push-out applications of these rules using this double push-out technique and string diagram rewriting in the presence of this special Frobenius structure. And indeed, let us make this precise. So we're going to use this slight extension of DPO, which is called DPO of interfaces. What it means that is essentially instead of rewriting objects, we are rewriting things of this form. So we're rewriting. So you can think of this J as some kind of a handle into G, right? This is the interface. So G with interface J will rewrite to H with interface J when there exists a rule, a double push-out rule, and again a double push-out diagram, but with these additional two commutative triangles down here. So this is essentially just saying that when I apply this double push-out rewrite, this interface kind of stays there. along the way. So it's a very slight change. And now let's make precise this correspondence between rewriting in S sigma plus frob and double push-up rewriting with interfaces in this prop of cospans. Okay, so I encode my rewrite rules as these double push-up rules, where you see that the interface, sort of the left and the domain and the codomain of the left and right hand side, that gets packaged up into this object in the middle, right? This is sort of the interface of this rule. And now there's a one-to-one correspondence between rewriting in this algebraic world over here in S sigma plus frob and double push-up rewriting over here in this category of hypergraphs. And the idea here is that the interface, the interface is the overall interface of the object you're rewriting. So I hope that now with these examples and these various visual representations, you're getting a feel for how this works.
So Paweł, maybe
yes.
before proceeding, I have another question from the chat, which is a little bit shy. So I will speak up for the chat. So they say, I have a quick question. Is there a precise rule for finding the complements?
Sure, but I don't particularly really want to get into it right now. So that this goes back to so there is a characterization of when complements exist. We also understand we also, for example, this category here of hypergraphs and hypergraph sigma, these are all adhesive categories. So we also know that these when push-outs sort of slightly better behaved than just if you're working with the universal property. So one of the things that we know, for example, is that if this guy here is mono, then if push-out complements exist, they're unique. So you avoid these kinds of situations. So this is and this is the fact that this is not mono is a necessary condition for it to be more than one push-out complement. For existence itself, you have to satisfy these things called gluing conditions. But yeah, these get quite concrete, so I don't particularly want to get into it. Thanks for the question. Right. So the final part of the talk is I want to tell you now how to get rid of the frob, right? Because we're interested, we don't want to carry around this assumption of always having a special Frobenius structure. We really want to understand how to do rewriting on vanilla symmetric monoidal categories, sort of on vanilla props, without the assumption of additional structure, additional algebraic structure, right? So we started off, the thing that I've showed you so far is the white part of this picture, right? I've showed you that DPO on this category of hip sigma is the same thing as rewriting in this SMC on free SMC on sigma with an additional special Frobenius structure, right? This is the part of the talk that you're already seeing. Now, what I want to do is sort of expand the worldview over here, which is rewriting sort of just vanilla SMCs, and understand what that's going to correspond to over here, right? So we kind of understood that for these examples, I hope that you got the flavor that DPO on these hypergraphs has this kind of special Frobenius assumption built in. So what we're going to have to do is to reduce the kind of DPO that I'm allowed to do in order to capture this correspondence. And this is something that we've called convex DPO rewriting. So I'm going to explain, I'll give you a flavor of the kinds of things that go wrong with sort of ordinary DPO, and we're going to discover various ways of fixing it, and eventually we'll get to this notion of convex DPO. Okay, so I told you about this theorem. So it's interesting to start maybe by understanding. So we have this coproduct diagram in the category of props. It will be interesting to understand or characterize precisely those cospans over here that are the image of something in S sigma, right? So that do not use the Frobenius structure. And I guess perhaps it's not particularly surprising that a cospan is in the image of this thing if and only if it is monogamous acyclic. Okay, so I'm going to explain what we mean by monogamous. I think acyclic is more or less clear. So monogamy means that every vertex in my hypergraph is either a left boundary vertex, so the thing that's picked out by the left leg of the cospan, or it has precisely one output tentacle attached. Now, every vertex is either a right boundary vertex or has precisely one input tentacle attached, right? So this is this idea that I'm not allowed to connect multiple tentacles to the same vertex, because that would be using this Frobenius structure, which we don't have. The boundary homomorphisms are monos, this is also related. So together, these three things tell you the concept of monogamy. And icyclicity, I didn't define path, but it's kind of intuitively obvious. Basically, there are no loops in my hypergraph. Okay, so these are not particularly difficult things to check, right? If you give me a hypergraph, I can check easily if it's monogamous or cyclic, and therefore I will understand if it's in the image of this map, of that injection. Okay, so let's now think about some particular concrete points where this double push-out construction can go wrong, can give us things that are not sound. Okay, so here we have a rule that, if you think about this as a string diagram, just says it replaces identity with F, with a thing, you know, a unary operation F, if you like. So here's a particular double push-out rule, right? So this is, we start off with alpha connected to beta. We've identified the match here. I'm going to match this guy over here. That has the effect of splitting up the alpha and the beta, and then I glue in the F in between, right? That seems fine. Now, the green guy here is the problem, right? Because I can do this in a different way. I can again split this up, but now I'm going to map the 2 over here and the 1 over here. Okay, and I end up with a guy. So I kind of glued this in this F in, but I've glued it backwards. So I'm not allowed to do this because in the string diagram, this would correspond to using the special Frobenius structure. and the way you can get around this is that you split up this boundary, right? So you remember this was the boundary of the rule. And the idea is that from that, you make this kind of cospan into the complement, this complement object that we've constructed. Okay, and here the monogamy definition is helpful, right? Because the original guy here ends up being monogamous, right? Because the 2 maps to this guy, the 1 maps to this guy. This satisfies the property of monogamicity, whereas this guy is not monogamous, right? I'm not allowed to map this input to this guy, which already has an input, which is alpha. Okay, and so essentially, when I can always do this, when I can find a map, when this map to this cospan to the push-out complement is monogamous, we call these things boundary complements. Okay, and to tie in back to the earlier discussion, boundary complements have the additional advantage of being unique when they exist. Okay, so we also get rid of this non-uniqueness issue, which it's not really an issue, but it just happens that boundary complements are unique when they exist. Okay, so that's one problem that we needed to take care of, but it's not the only problem. There's another problem, which is this problem that we can have illegal matches. Okay, so let me give you a little example here. So this is a rule that I would like to encode, let's say, from a rewrite system on a prop. So whenever I find something like this, I can replace it with this, right? So now let's encode this as string diagrams and see where we can go wrong. So this is we encode this as hypergraphs, and we're going to use double push out. So there's a weird thing happening over here, right? So this is a legal match, although it kind of feels like it should be illegal. And in fact, we do make it illegal, but let's understand why we should make it illegal, right? So this is a match, but you see, I'm mapping this through over here and the 0 over here. Okay, and now when I perform the push-out complement, the push-out, I end up with this right-hand side. Now that wouldn't happen just in a vanilla symmetric monoidal category, right? You can maybe picture in your head what you'd have to do. You'd have to kind of pull these two wires over here past each other in order to get something that looks like this guy, right? So here I would have to use this special Trebenius structure. And the property that's important here is this property of convexity, right? So what does the property of convexity say? Well, essentially here, if I look at this match is not convex, right? Because there's a path from 2 to 0 inside the target hypergraph that's not in the image of the match. So a convex match should be something that if I'm within the match, there shouldn't be paths which are not in the image of the left-hand side. So this is not a convex thing, and a convex match is something which is both mono and has this image convexity property. And that's basically it, right? So rewriting in a sigma in this, and just a vanilla free symmetric monoidal category on sigma is just this notion of convex DPOI rewriting, right? So if I can get from A to B, that means I can come up with over here in the world of hypergraphs with a double push-out rewrite. And this has to satisfy the conditions, right? So we are rewriting monogamous things with convex matches and boundary complements. And of course, none of these things are particularly difficult algorithmically, right? It's very easy to check if something is a convex match. It's very easy to check if something is a boundary complement, right? This is not difficult. So that essentially is what I wanted to say. So I think I'm a little bit over time already anyway. So let me just tell you about some other stuff that's happened since. So this is a paper that we had at LIGS 5 years ago now, rewriting modulo symmetric model structure. So we've examined some, we have some theorems about confluence in these kinds of graph rewriting of interfaces, which is useful, right? Because you can see how much of classical rewriting theory, things like checking critical pairs, etc., how much of that can be lifted to this setting, and there are surprisingly a lot of similarities with sort of classical rewriting theory. We also kind of did at LIGS 2018 we had a paper which we did the multi-sorted version of this essentially, right? So we have sort of several Trebenius structures interacting. And recently we've been writing this up sort of as general papers. So we have these 3 papers which develop this entire story. 2 have already been submitted, and the 3rd is going to be submitted at the end of this month. And I think that concludes my talk. So thank you very much for your attention.
Thank you, Paweł. Thank you for your talk. And so we have our round of silent applause. So people are silent applauding you. And so if someone has questions, this is question time. You can just unmute yourself and ask your question. Let's check the chat. There is one. Okay, so there is one question, Paweł. Can you see the chat, or you want me to read it?
I can try to, I don't see how I can open. Oh, no, hang on, maybe it's not this more. Yeah, okay. I think, yeah, I can see it now. So who's asking? Robin?
Yes.
Hi, Robin.
Oh, I see. Matteo has said something very intelligent. So we should read it for the recording. So the question is, what about the compact closed case without Trebenius? Does it reduce to the hypergraph case without all the side conditions required to prevent the pathological matches that arise?
It's a good question. I don't immediately see the answer, but it will be interesting to work out. I guess I think that might be the case. I think with just the compact closed, it'd still be okay because we kind of implicitly. Yeah, I think my conjecture, which I could be wrong, is that it would work without all these side conditions. Because somehow implicitly with this encoding, I didn't want to do that. Let me just go back to the way. Yeah, so I was thinking about the self-dual case, yeah. But essentially the way that, which is the slide that I want, okay, this slide. Essentially here, there's already a kind of a compact closed thing going on, right? Is that what I'm really doing here is these guys are kind of like as if I bent the I around, right? Because I'm bundling I and J into the same boundary point, together into the boundary. Maybe you'd still have to be a bit careful with this boundary complement business. But yeah, it's a good question. I need to think about it some more.
So we also have a question from Francesco. Francesco, would you unmute yourself? No, from Fabrizio. I'm sorry, I misread.
Okay. No worries.
Sorry, my fault. I misread.
So, hi, Paweł. My question will be, I guess, general and unwavy, but basically, if I understood things correctly, you say very vaguely, okay, I have a string diagram in some category that can be presented in some way. I have some ways, equations that I can do surgery with. I consider the diagram as an hypergraph. And basically, I translate the equations that present the monoidal category into hypergraph rewriting rules. I feed everything to a computer and I'm very happy. Now, my question is, as also Daniele mentioned before, hypergraphs are actually the underlying structure of a prenet. So a prenet is nothing more than an hypergraph with some token rules and notion of markings and stuff like that with a dynamics on it. And now prenets do present themselves free symmetric strict monoidal categories. You can just define all the runs of the nest to be your morphisms. So the question I have is there a relationship between these two things? Because it feels to me that these are quite different ways of using hypergraphs. And I always felt they should be related in some way, but I don't know if anyone ever really tried to work this out or if my intuition is just not correct.
Sorry, don't they precisely represent strict monoidal categories, not the symmetric ones?
It's the same. You can adjoin symmetries freely, and depends on the token philosophy you are interpreting, but there's no real difference actually.
Yeah, I mean, so I guess it's kind of there's a slight difference in flavor here, right? Because with prenets, what you're really doing is you're setting you're thinking of basic rules for computation as these, let's say, the specification of what the transitions are in the Petri nets, and then the free symmetric model, the free model category or symmetric model category generated from this is some kind of
is the trace of the
it's a computation, right?
Yes.
Okay, so it's true that here I'm interested in the free thing generated from such a signature. So let's say I'm interested in a category if you use the Petri net language in which the arrows would be computations. But here I really have a rewrite system on the computations, right? So there's a certain computation which looks like a unit fed to a monoid transition, right?
Mhm.
I want to rewrite that entity. So it's that kind of rewriting I'm doing.
Yeah.
Which there might be some, of course, I don't know, there might be some interpretation in Petrinet theory, but it's not entirely clear.
Yeah, I was just wondering if there was a formal relationship of some sort between these two things, because they feel indeed very different. But since the underlying structures are very similar, I would expect, some kind of formal link to be there,
Sure.
buried somewhere, but I don't know. Okay.
It seems to me that doing rewriting on pre-net-like stuff or Petrinet-like stuff, it's like maintaining the some kind of extensionality of the whole system in the sense of it computes the same thing, but maybe you're optimizing it or just rewriting it in some way.
Yeah. I mean, so there could be a something interesting that this says about Petrinet. So I don't know off the top of my head, but yeah, that sounds interesting. That sounds like a reasonable thing to look at.
Cool. Thanks.
Thanks,
Okay,
Elise.
I would say I have to close.